Hello, everyone. Hello, my friends. I am Professor Marco Santos. I teach operational research at Military Institute of Engineers. And today, I'm going to talk about the TOPSIS method. And I think the TOPSIS method is one of the most used methods in the world. So let's see my presentation. So here, TOPSIS method. TOPSIS, the word TOPSIS means technique for order preference by similarity to ideal solution. This is an acronym. So here you can see a little bit about my history. I have been working in the Navy for 28 years, and I made my master degree in 2010, and I finished my PhD in 2018. So today I teach operational research at Military Institute of Engineers, and I teach data science and analytics at São Paulo University. So let's see our summary. We have an introduction. I'm gonna talk about multicriteria analysis, TOPSIS method. TOPSIS method, step by step in 7 steps. Some applications, some possibilities, and the computational tool named tree decision method that we developed here at Military Institute of Engineers. So through our lives, we are forced to make a series of decisions. Some are easy and some extremely difficult, extremely hard. Whether easy or difficult, in order to make a choice, we usually have alternatives to be chosen according to a set of predefined criteria. A simple example might be choosing a car to buy. Most people consider price, engine power, manufacturer reputation, comfort, and so on. These are nothing more than our criteria for choosing a car, and based on them, we evaluate our alternatives depending on which criteria are most important to each person. Now, imagine a more complex decision to be made, such as buying an apartment, purchasing a new warship for the Brazilian Navy, or even choosing a city to be bombed in case of war. I remember once I I read the history about atomic bomb, about the Second World War, and the scientists developed the nuclear bomb, but they don't know where they will drop the bomb. So imagine the situation, extremely complex situation to choose a city to be bombed with a nuclear bomb. So wait, hold on a sec here, okay. Multi-criteria decision-make problems are characterized by a decision matrix which is composed of alternatives and criterion weighted according to the decision maker in question. Methods to solve MCDM problems have been widely used to select the best alternative among a finite number of alternatives. As an example of methods, we can mention AHP, ANP, Prometheus, Thor, SAPIVO, and TOPSIS. So, and there is a structure in every problem involving multi-criteria analysis. This is the structure. We have a number of criterion 1, 2, 3, 4, 5, 6, 7, and whatever you want. And we have a set of alternatives. Alternative 1, alternative 2, 3, 4, 5, 6, whatever you want. So I need to apply a method. I will construct a decision matrix with the data set from this structure. I will apply a method, a mathematical model, this model. So with this model, I can calculate, I can find the results, the solution, the problem solution. And wait a moment, well, can I look here? Oh my goodness. Okay. The TOPSIS algorithm was developed by Wang and Yun in 1981 and is a technique for evaluating the performance of alternatives through their similarity with an ideal solution. According to this technique, the best alternative is the one closest to the ideal solution and farthest away from the non-ideal solution. So, look at the main idea about this method is here. According to this technique, the best alternative is the one closest to the ideal solution and farthest away from the no ideal solution. So look at this picture. Look at this picture. You can see here ideal solution. So in this case, the best alternative is the one closest to ideal solution. So I have alternative E, B, C, D, and E. In this case, the best alternative is C, because alternative C is closest to ideal solution. And if I look at anti-ideal solution, I will see the same alternatives, E, B, C, D, and E. And the farthest away, the farthest alternative is alternative D. D is the farthest alternative from anti-ideal solution. But now I need to understand what is ideal solution and no ideal solution. So I'm gonna write in here what is ideal solution and no ideal solution. This is the question. Let's understand. So we will see now that we have many equations in TOPSIS method. So we have all these equations. Don't worry, I will explain step by step the method, and I will calculate the result by hand, step by step. Don't worry, it's very simple, very easy, these equations. So let's understand the general idea about the TOPSIS method. We have 7 steps, and I will calculate step by step. First, decision matrix definition. We always need a decision matrix to start the problem at the beginning. Second step, decision matrix normalization. Third step, weighted normalized decision matrix construction. The next step, determination of the positive ideal solution and the negative ideal solution. So this is ideal solution, the same meaning here. Positive ideal solution is ideal solution A plus positive A and negative ideal solution is the same meaning of non-ideal solution. Same meaning. No ideal solution. Same meaning. Next step, distance, measurements, calculation. Next, relative proximity calculation. And at last, ordering preference. So let's see a hypothetical example, totally hypothetical. Let's consider a matrix D, which consists of alternatives and criteria described by. So this is the first step. I need the decision matrix. Decision matrix. So, for example, I need to select internet provider, for instance. So first, I have the criteria. So we have, for instance, cost, deadline, deadline installation, and, for example, velocity. And I wish low cost, low deadline, and a high velocity. You know? So, and we have, for example, 3 alternatives. 3 alternatives. For instance, provider 1, provider 2, and provider 3. But look, we can work with more if you want. You can work with more criteria. Criteria 4, 5, 6, 7, whatever you want. And you can work with more provider. Provider 4, provider 5, provider 6, provider. Your decision matrix can be one matrix M by N. M and N can be any number, and you can have M rows and N columns. So let's work with 3 lines, 3 alternatives, and 3 criteria, 3 columns. So in this case, we have provider 1, provider 2, and provider 3. Here the rows, we have the alternatives. And here, in columns, we have the criteria. Here we have cost, deadline installation, and velocity. And we can, and in this case, we can, we wish a low cost, a low deadline installation, and high velocity. And I need fill out this decision matrix. So, for instance, we have 90 units of cost and 120 can be dollars or any unit. 120 and 70 units. And here, for instance, in deadline installation, we have, for instance, 20 hours, 8 hours, and 12 hours. And at least velocity, we have 80 megas, 100 M, and 90 M. So we have the decision matrix, and I finished the first step with the decision matrix, fulfilled decision matrix, you know? Okay, can I go on? Okay. I will explain about the method very slowly, very slowly, step by step. I hope you understand the method step by step. So I wanna calculate step by step each detail, because I wish you understand the method. So matrix D, once filled, needs to be normalized to a matrix R. This allows comparison between all criteria, because I can't compare different units. If you watch this matrix, you can see I can't compare cost with deadline installation and velocity. It's impossible, because we have different units. That's why I need to normalize it. The matrix needs to be normalized, because all units will disappear. So let's calculate the vector norm. So this is the expression about vector norm. Vector norm. So we have norm equal square root sum I equal 1 to m x I j square. This is the expression of vector norm. So let's calculate the vector norm, the cost vector norm. Cost is. So I will change the color of my pen. For instance, here we have cost. Cost. The vector norm will be square root of 9 square plus 120 square plus 70 square. So let's calculate. We have square root of 9 square plus 120 square plus 70 square. Here we have 9 by 9, 81, 00, 144, 00, 49, 00, equal the square root 27,400. It is approximately 165.53. Okay. And the next is deadline vector norm. Norm deadline square root. Let's come back a moment. Here we have, follow my train of thoughts. First, I calculate square root of 9 square plus 120 square plus 70 square. Now, the vector norm of deadline installation will be square root of 20 square plus 8 square plus 12 square. Very easy, very simple. So let's calculate. Square root of 20 square plus 8 square plus 12 square. 464, 144. So we have square root of 608, approximately 24.5 6. Okay. And at least we will calculate the vector norm of velocity. The square root. And now we will follow the same train of thoughts. Velocity here. Velocity here. Here. The square root of 80 square plus 100 square plus 90 square. So let's calculate here. Square root of 80 square plus 100 square plus 90 square. So we have a square root of 24,500, approximately 456.52. Okay. I don't finish it, the second step. I just calculated the vectors norm. I don't calculate the decision matrix normalized yet. So let's continue the second step. We have values RIG equal XIG over the square root sum I equal 1 to m XIG square. So notice that this fraction is the vector norm. And we already have these values about cost, deadline installation, and velocity. So now we have less work to do. Let's calculate the value R11. We have X11 over vector norm of cost. So we have X11. If we came back here we have X11, where X21 and X31. Here, X12, X22, and X32. And the last column we have x1, 3, x2, 3, and x3, 3. Okay? So x1, so I'm sorry, R1, 1 is equal x1, 1 over norm, vector norm of cost. So we have x1, 1, 90 over vector norm of cost equals 165.53 that we calculate here, the norm cost of the vector norm, the cost vector norm. So let's continue. We have 90 over 165.53, approximately 0.54. And R21 is x21 over cost vector norm. So we have 120 over 165.53 equals 0.73. And R31 equals x31 over cost vector norm. So we have 70 over 165.53, approximately 0.4. Hold on a second, sorry. Okay. Oh my goodness. Here. 0.42. Okay. Now, here I finished the first column, the cost column. Now I will calculate the second column, the column of deadline installation. So R12 is equal x12 over vector norm of deadline vector norm. So we have 20 over 24.66 equals 0.81. And now R22 is equal x22 over vector norm deadline vector norm is equals 8 over 24.66, approximately 0.32. And now 3, 2 is x 2 over that vector norm. Is 12 over 24.66 equals 0.49. And the last column is, here we have cost, here we have deadline installation, deadline, and here we have velocity. So R13 is equals x 13 over velocity norm equals 80 over 156.5.52. R13 is approximately 0.51. The next R23 is x 23 over vector norm, velocity vector norm. So we have 100 over 156.52 R23 is equal 0.64. And at least R33 is equals x 33 over vector norm, velocity vector norm. So we have 90 over 156.52 equals 0.58. So now we finish it. The second step. I have the decision matrix normalized. I'll construct the decision matrix normalized with all values together, and you can see. Let me take a little water because I'm thirsty. Oh my goodness. So I hope you understand the TOPSIS method. I am calculating step by step each expression very slowly because I wish you understand the method. So let's continue the next step. Now, we need the weighted normalized decision matrix. So let's see the matrix with normalized matrix. So we have these values: 0.54, 0.73, 0.42, 0.81, 0.32, 0.49, 0.51, 0.64, and 0.58. I'll put all these values together. So we have the decision matrix normalized is RIG is equal 0.54, 0.73, 0.42, 0.81, 0.32, 0.49, 0.51, 0.64, and 0.58. Okay. Here we have the decision matrix normalized. So now I need the weights. For example, in this case, we have 3 weights: W1, W2, and W3. And for instance, I have W1, 0.5, W2, 0.3, and W3, 0.2. Look at here, we have 50%. Here we have 30%. And here we have 20%. You know? And if I sum these values, I always have to get 100%. So I can take, for instance, 6%, 20%, and 20%. The sum is 100. I can take 10%, 45%, 45%. In this case, 100%. The sum is always 100%. Okay. So now we will take these numbers. W1 equals 50%, W2 equals 30%, and W3 equals 20%. So now I will multiply each weight by the values in your column. So now W1 is 0.5, and I will multiply by 0.42, 0.73, 0.54. Here we have this matrix P is the weights times the values from the normalized decision matrix. So I need this matrix, weighted matrix normalized. So this matrix became 0.5 times 0.54 equals 0.27, a half. 0.5 times 0.73 is 0.37, and 0.5 times 0.42 is equal 0.21, a half. So now the second weight, I will multiply for all values in the second column. 0.3 times 0.49, 0.32, and 0.81. So 0.3 times 0.81, I have 0.24. 0.3 times 0.32, I have 0.096. And 0.3 times 0.49, I have 0.147. And at last, I have 0.220% times 0.51, 0.64, and 0.58. So I will have 20% times 0.51 equals 0.102. 0.2 times 0.64, I have 0.128. And finally, I have 0.2 times 0.58, I have 0.116. And I finished this step. Now I have the weighted normalized decision matrix. Normalized decision matrix I have here. And now I I have the weights W1, W2, and W3, and now I have the weight normalized decision matrix. I have the matrix EIG. And now I finished the third step. Is it okay? Got it? Okay, let's continue. Fourth step, positive ideal solution and negative ideal solution determination. In general, the criteria are classified into two types: cost criteria, the lower the rating, the better, and benefit criteria, the higher the rating, the better. Returning to our provider purchase example, price is a cost criterion. That is, the lower the price, the more desirable the provider is. On the other hand, the velocity is a benefit criterion. That is, the bigger, the better. So we have a trade-off. So we need to identify the positive ideal solution for benefit criteria and the negative ideal solution for cost criteria, as shown below, where P plus is max PIG if the criteria is of benefit, and minimum PIG if the criteria is of cost. And P, negative P, is minimum PIG if the criteria is of benefit, and maximum PIG if the criteria is of cost. So, in other words, the previous equations shows the best performance in each criterion, be it cost, in which case the best performance is the lowest value, or benefit, in which the best performance is the highest value. And assembly the vectors positive E and negative E, which are nothing more than the performance for a perfect alternative. That is, having high ratings for the benefit criteria and low rating for the cost criteria. So I was very careful in this explanation. So we need to identify. Oh, here we can write here. We need to identify what is E positive E values and negative E values. So we have our matrix here. Our matrix is here, here, PIG. Okay. I will rewrite this matrix in on the next slide, on the next screen. Okay, here. So we have provider 1, provider 2, and provider 3. Okay, and in columns, we have cost, deadline, and velocity. Okay, and we have 0.27, 0.37, and 0.21. 0.24, 0.096, 0.147, 0.102, 0.128, and 0.116. So now I can figure out a positive E and negative E. So positive E is 0. We have 0.27, 0.37, and 0.21. What value is my best value? I ask you. The best value is 0.21. Why? Because the cost is a cost criterion. I wish pay I wish low values. So, and the negative E is the higher cost. So we have 0.37. And in deadline column, what is the best value? The best value, deadline, I wish here, I wish a low cost. Here, I wish a low deadline. So the best deadline is 0.096. And the worst deadline is 0.24. Okay. And velocity is a benefit criteria. So I wish the higher velocity. So the best velocity is 128, 0.128, and the worst 0.102. So now I finish this step. You know, okay? I finished this step with the positive ideal solution. Here we have the positive ideal solution, and here we have the negative ideal solution. Okay, now we can continue. So, next step. Now, we must calculate for each alternative the Euclidean distance of each rating for the vector of positive solutions, positive A, and for them the negative ideal solutions, vector negative A. So these expressions are a little bit weighed. These expressions are a little bit worried. It seems so hard, but I will calculate step by step, and you will see that the calculus is very simple, very, very simple. It isn't complex, it isn't hard. So let's calculate the distance calculate. Okay, let's see. Positive distance. So we have, let me write the matrix here. So we have provider 1, provider 2, provider 3, 0.27, 0.37, 0.21, positive A, negative A, 0.21, 0.37. Here we have cost. Deadline. 0.24, 0.096, 0.147, 0.096, 0.24. And velocity, we have 0.102, 0.128, 0.116, 0.128, and 0.102. Okay. So now I can calculate these values, positive D. Let's calculate. This expression means d plus d positive d is square root sum vector v minus e plus square Euclidean distance. So let's see. Provider one, we have d positive d1 is following my pay attention and follow my train of thoughts. Positive d1 is square root. So we have 0.27, the value, minus here we have the ideal solution, positive. Look at this expression. E positive E is our reference now. We have positive D, and now my reference is positive E. So now, to provide the one, I will take 0.27 minus 0. My provider is here. So I need to calculate Euclidean distance with this reference. So this is the difference. Here we have the difference. So 0.27 minus 0.21 square plus 0.24 minus 0.096 square plus 0.102 minus 0.128 square. And now you can use the calculator on your computer. So you will find approximately 0.158. So provider 2, I have D plus 2, provider 2. We have the same thoughts, 0.37 square root of parentheses 0.37 minus 0.21 square plus 0.096 minus 0.096 square plus 0.128 minus 0.128 square. Exactly the same way. So we have the square root, what's my pen over here? Square root, we have 0.37 here, so minus 0.21. Square plus 0.0996 minus 0.096 square plus 0.128 minus 128 square. Look at here, we have 0, and here I'm gonna take 0. So I have 0.16. And at last, I have provider 3. Provider 3, positive D3, square root, exactly the same way. I have the provider 3 and square root 0.21 minus 0.21 square plus 0.147 minus 0.096 square plus 0.116 minus 0.128 square. This is I will find the result. So I have 0.21 minus 0.21 square plus 0.147 minus 0.096 square plus 0.116 minus 0.128 square. And here we have, I'm gonna take 0, and if you calculate with the calculator in your computer, you're gonna take 0.052. Okay, now we finished the positive D's, but now I need to calculate the negative D's. So let's calculate, no problem. We have exactly the same way. So let's calculate the negative D. So I need again the decision matrix, the weighted decision matrix. So we have provider 1, provider 2, provider 3, and here we have cost, deadline, velocity, and 0.27, 0.37, and 0.21. And 0.24, 0.096, 0.147, 0.102, 0.128, and 0.116. But now I need only the negative ideal solution. I don't need the positive ideal solution because I'm going to calculate the negative d. So I need negative ideal solution, no ideal solution. So I have 0.0.37, 0.24, and 0.102. This is my reference now because I'm calculating the negative d, this Euclidean distance with the negative e reference. So let's calculate the distance. The distance of either one from negative e. So I have d1 negative d1 is square root, same, let's follow the same train of thoughts. 0, negative, okay. So, where is my pen? Here. 0.27 minus 0.37. 0.27 minus 0.37 square plus. Look at this table. 0.24 minus 0.24. Square plus 0.102 minus 0.102 square. So here, I'm going to take 0, and I'm going to take 0, and now I have 0.10. So negative d2 divided 2, exactly the same way. Square root 0.37 minus 37 here, minus 0.37 square plus 0.096 here, minus 0.24 square plus 0.128 minus 0.102 square. So here I'm going to take 0, and now I have 0.102 146. And at last, I have negative D3, provider 3. The same way, square root 0.21 minus 0.37 square plus 0.147 minus 0.24 square plus 0.116 minus 0.102 square. So if you use your computer calculator, you will take 0.186. Okay, so now we are almost finished the method. You can see you need to make so much calculus. The method is very hard, but we have a simple method, but the method is very how can I say, workful. I don't know. We have so much work if I calculate the result by hand. And now, the next step, be careful because we need to calculate the relative proximity. Because look at this picture. Here we have the ideal solution, positive E. And the alternative C is the closest to positive E. So I can think of alternative C. I have alternative E, B, C, D, and E. So, like alternative C is the closest to ideal solution, probably the alternative C is the best alternative. But look, if I think about the negative ideal solution or no ideal solution or anti-ideal solution, the best alternative is the farthest away. So if I look the alternatives E, B, C, D, and E, the farthest alternative is D. So if I think about the ideal solution, the best alternative is C. But if I look at negative ideal solution, the best alternative is D. And how can I find out the best alternative? That's why I need to calculate this expression. This is a Greek letter called C. C equals negative D over positive D plus negative D. So let's calculate this expression. Relativity proximity. Having calculated the distance from the previous step, the next step is to determine the relative proximity. The idea is to choose as the best alternative the one closest to the positive ideal solution and farthest from the negative ideal solution. So this is the idea, the main idea about the method here. So let's calculate. The last step is to rank the alternative based on the vector C. The best alternatives are those with the highest values of C and should be chosen as they are close to the ideal. So let's calculate the results. So I have provider 1, provider 2, and provider 3. And positive D, we calculated 0.158, 0.106, 0.052, and negative D, 0.100, 0.146, and 0.186. And now I can calculate the relative proximity. Relative proximity. So relative proximity 1 is, look, negative D over positive D plus negative D. So we have negative D, 0.100 over positive D plus negative D, 0.158 plus 0.100 equals 0.39. Next, 2 is negative D, 0.146 over the sum, 0.160 plus 0.146 equal 0.48. 0.48. And at last, 3 is negative D, 0.186 over positive D, 0.052 plus 0.186. So I have 0.78. 0.78. So this is my result. This is my result. This is my result. So now I can finish the method. The last step is ordering the preference. So I have the relative proximity. Relative proximity. I have provider 1, provider 2, and provider 3. 1 is 0.39, the next 0.48, and 0.78. And now it's possible to ordering the alternatives. So here we have the first, the best alternative, and 0.48 is the second alternative, and 0.39 is the worst alternative. And now we finish the method. And you can see the expression. I think the expressions are simple, but I need to work hard to calculate. And you see, we work on a very simple decision matrix with 3 rows and 3 columns. Only three rows and 3 columns. Imagine a problem with, for instance, 10 rows and 20 columns. It is a completely absurd. It's so hard to calculate. So today, I calculated a very simple decision matrix. So with this method, we can calculate many different problems, real problems, operational problems, tactical problems, strategic problems, and I have written many papers with my students at Federal Fluminense University and at Military Institute of Engineers. I think dozens of papers using this method with my students. All kinds of problematic situations, I can use this method, TOPSIS method. So let's see some papers. Comparative study of the analytical hierarchy process and TOPSIS techniques for them site selection use GIS. Here we have another problem. Critical data delivery using TOPSIS in wireless body area networks. And here we have another paper combining TOPSIS with group end value method for wine evaluation model. So let's solve another problem. So I believe that we need practice to learn everything. It's impossible to learn about a subject. It's impossible to learn about a method if we don't practice. So let's see our example. At first, let's construct a decision matrix. So we can think about cell phone. For instance, for example, I need to buy a cell phone, for example. And I'm gonna think about the criteria. For instance, I have cost, battery, cost in dollars, United States dollar, battery, time, in hours, and storage. I can think about camera, resolution, camera, megapixels, and let me think, storage, maybe storage. Storage. Capacity. Maybe capacity, storage. I don't know. Storage. Storage. Okay, no problem. Storage. Enjoy it. So, gigabytes. And for example, I have the alternatives. iPhone, Samsung, and Motorola. Look, pay attention. This is only an example. It isn't true. It isn't true. Only an example. So, so let's see. So now I have the decision matrix. The decision matrix. Decision matrix. Rows, I have iPhone, Samsung, and Motorola. Gross. And in columns, I have cost, for example, iPhone, $800, Samsung, $700, Motorola, $450. Okay. Battery, iPhone, 24 hours, Samsung, 20 hours, Motorola, 18 hours. Okay. And camera, 6 megapixels, 50 and 64. And at last, storage. Storage, 512, 256, and 256. Okay. Now I need the weights too, because without the weights, I can't calculate the TOPSIS method. The weights are necessary to calculate the equations. So we need the weights. Weight, cost weight, battery weight, cost, weight, battery weight, camera weight, and storage weight. So for instance, I can say cost 4%, battery 30%, camera 10%, and the storage 4%. Look, here, pay attention. The sum has to be 100. So I have 4 plus 30, 70, 70 plus 10, 8. So I need 20%. So the sum is 100. So this is enough. I have all the data set to calculate the TOPSIS method. So you can say, Professor, oh my goodness, it's impossible. I watched how you calculate the example before that, and the example that you solved it with 3 lines and 3 columns, it was so hard. Imagine this example with 4 columns. It's harder than the another example. But take it easy. Take it easy. Calm down. So here at Military Institute of Engineering, I coordinate a research line a research group where we develop computational tools with the purpose to allow that everybody can use this method. Because I know many people can't use this method because the math is very hard. So we developed these tools where you only need the decision matrix and the weights only. Even if you don't know any equation about TOPSIS method, you can use it because we developed this tool called 3 decision methods computational platform. So you can type www.3decisionmethods.com. Okay, got it? So let's see how it can work. So 3 decision set. 3 decision methods. Okay. Here you have 3 decision methods. So first, you have to choose the method that you want to use. Analytical hierarchy process. Another time, I will give you a class about analytical hierarchy process. So we have analytical hierarchy process, TOPSIS method, and HP TOPSIS to N. This method, HP TOPSIS to N, you can find here in our YouTube channel, Operational Research House. So let's use the TOPSIS method. Like I said, you just need the decision matrix and the weights of each criterion. So first, TOPSIS. So give your analysis a name. Cell phones. Cell phones, confirm. Okay. So alternative 1, iPhone. Alternative, first step, we need only three steps to calculate all equations. So iPhone, second is Samsung, and add alternative and Motorola. Okay. You must click here, next. Second step, criteria name. First criteria, cost. Okay, add criterion. Battery, add criterion. Camera, add criterion. And storage. Okay, Second step, next. And the last step, criteria values. I need to fill out the decision matrix. So, cost, iPhone, $800, Samsung, $700, Motorola, $450. And the weight is 40%, 0.4. And I wish maximize or minimize the cost. I wish minimize, so minimize. Next, criterion battery. iPhone 24 hours, Samsung 20 hours, Motorola 18 hours, and the weight is 30%, 0.3. And I wish maximize or minimize the duration, the battery duration. I wish maximize. Okay, the default is maximize. Next, camera. Camera is 60, 50, and 64. Weight is 64, weight is 10%, 0.1. And I wish maximize the camera or minimize. I wish maximize. Okay, the maximize is default. And storage. Storage is 512, 256, and 256. And the weight is 20%, 0.2. And I wish minimize or maximize. I wish maximize. I have a benefit criterion. So look, the sum is 1, equal 1. Okay, it's all right. So we have 3 steps. First, the criteria set. Second, the alternative set. And the last is I need to fill out the values in decision matrix. So now submit. So we have the result here. The result here. We have Motorola is the best, the first place, the best cell phone. iPhone is the second, and Samsung is the worst cell phone. So how you can see, as you can see, I can use TOPSIS method even if I don't know any equation, I don't know any mathematical expressions. It's possible to use TOPSIS method even if I don't know any expression. So you watch it, that I needed almost 2 hours to calculate the result from the decision matrix 3 by 3. Very small decision matrix, 3 by 3. I needed almost 2 hours to calculate all expression by hand. So now you can see I am analyzing a decision matrix with 3 lines and 4 columns, 3 rows and 4 columns. And I think I spend less than 5 minutes to calculate. And I can calculate even if I don't know any math, any expression, you know? So we developed this tool, this software here in my lab at Military Institute of Engineering. Very simple, very, very amazing. And you can see more details if you click in this symbol plus. You can see the decision matrix with the weights, you can see. And if you click in this save as PDF, you can save your project here. You can save and you can see in another time. So, let's return to our presentation. So here, okay. Here. So this platform is totally free. You can use in United States, France, Ireland, wherever you are. United States, Mexico, Brazil, and France. This platform is totally free and totally open. You need just type www.3decisionmethod.com. Okay. So I'm finishing my class today. If you look the equations from the TOPSIS method, I'm sure you are thinking, oh my goodness, how can I calculate all these equations? How can I work with this absurd? It's impossible to use the TOPSIS method. But with the tool that I developed with my students in computer science at Military Institute of Engineering, oh, dude, it's very simple, very easy to use TOPSIS method. I love 3-decision methods. I love 3-decision methods too. Thank you very much, Professor Marcos. It's very simple, very easy to use TOPSIS method. So, oh my goodness, oh dude, no dude, I can't use TOPSIS method, it is impossible. It's impossible to use TOPSIS method. I'm sorry. But if you see my tool, my software, it's very easy, very simple to use. the TOPSIS method in only 3 steps: the set of criteria, the set of alternatives, and the decision matrix values. You can calculate all the results from the method. Very simple, very fast, and I wish you join my software, and I hope that I can help so many people all around the world. So this is the reference. The first reference is the main reference about the method. The method was written by Wang and Jung in 1981. And that's it. Thank you very much. And there are my contacts. If you have a question, you can send me a message on my LinkedIn. If you scan this QR code, you can connect with me on LinkedIn. So you can send me a message on my LinkedIn. This is my ResearchGate. I have a ResearchGate with more, I think I have more than 700 papers, published papers, more than 700 with every kind of method from operational research. And my email, you can, if you wish, you can send my email too. So that's it. Thank you very much for watching my video. And here on Operational Research House, my channel on YouTube, you can find almost 400 different methods from operational research. So travel and sales main problem, kill theory, and many others, critical path method, and many others methods. So if you join my video, give me a thumbs up, give me a subscribe on my YouTube channel, and I really hope that you join my video. So that's it. Thank you very much, and bye-bye.